Good evening. I had forgotten to start the record button during the second session of the class today. To cover for that, I'm going to record now section 6.4. So we'll go through it and talk about it and get it all done. So let's get started. Okay, so section 6.4, we are talking about the general exponential and for sure I'll just put logarithm functions. Okay, so in 6.2 we learned about the natural logarithm, and in 6.3 we learned about the natural exponential. But now we are going to expand this definition to a general exponential and a general logarithm. So what that means for us is that I want to take, for example, we're going to start with the general exponential here. And I'm going to start with y equals b to the x. Okay, so b here is not just e, but b is any number which is greater than 0. Okay, which that number needs to be greater than 0 because, I'll talk about more in a sec. You can kind of imagine if I said negative 1 to the x, for example, you're going to have a lot of issues because what if x is 1/2? Or what if x is 1/3? 1/3 wouldn't be too bad. 1/4 though, like you're going to get the complex numbers, and we have a lot of issues, so we don't want to use that. So instead, we need to make sure our b is greater than 0 at all times. Okay. Also, what we're going to do, right, is I want to be able to understand this function in context of e to the x, and so that's what I'm going to do. I'm going to rewrite b to the x as e to the x times the natural log of b. Now, if you're confused why this is true, let's kind of think through it real fast, right? So remember, e to the natural log of x is the same thing as x, right? So of course, if I just replace this with b, then I get that b is equal to e to the natural log of b. Now this is okay, right? Because b is greater than 0, and if any number greater than 0 is allowed to be plugged into the natural log. You can't put 0 or anything less than, but so this works out. Now, remember also our rule with e, that if I take e, let me write this differently. No, I'll do that. If I have e to the x, and then I raise it to some r power, right? Or if I take e to the r and raise it to some x power, right? What's going to happen is this is going to end up being e to the x times r, or r times x, right? Basically, I can take the powers and I can multiply them together. So that's exactly what happened in this instant, is that I am taking e, so I rewrote b as e to the natural log of b. So b to the x equals e to the natural log of b of x, or raised to the x power, but then the powers can multiply together, so I get e to the x times the natural log of b. Okay, so that's where this comes from, and this is kind of the setup for our formal definition here of what I'm going to call b to the x, right? So it's kind of founded off of e to the x, and we build from there. Okay. So with that being said, we're going to kind of take this and play around with it a little bit. What we're going to see is that this b to the x function, where b is greater than 0 at all times, is always, it satisfies the same exact rules that e to the x does in general, right? So remember, we had that e to the x plus y is equal to e to the x times e to the y, and we had e to the x minus y equals e to the x over e to the y, and we had e to the x, the one we just talked about, to the r, equals e to the r times x. And these ones have the same commonality with just the b as well. It doesn't have to be e. B to the x plus y equals b to the x times b to the y. B to the x minus y equals b to the x over b to the y. And b to the x and then raised to the r power is going to be e to the r times x, just like that. Okay, good. So let me real quick just demonstrate to you, convince you that this statement right here is true, at least, and then you can kind of think about the other ones. So if I'm going to take b to the x plus y, and I'm going to rewrite that using our definition up here as e to the x plus y times the natural log of b. Okay? But this is the same thing as e to the x plus y to the natural log of b, right? And that just comes from, remember, if I have e, then I can split up the powers. E to the x plus y, we know for a fact is the same thing as e to the x times e to the y, and then to the natural log of b power, right? Now, these are both e's, right? So what I'm going to do is this natural log of b can distribute to each term inside. So I'm going to be left with e to the x ln of b and then e to the y ln of b. Essentially, that ln of b is going to multiply both terms. Okay? But literally e to the x ln of b is x, or b to the x, and e to the y ln of b is y. So this concludes kind of a little proof of that statement. Okay? Now, to mention this one real fast, which just kind of produces itself, just comes naturally from everything else we've already discussed. But just to make it clear, it is also true that if I have two different bases, let's say I have a base A and a base B, and I multiply them together, similar to what's happening here, and then I raise it to some x power. Now this is the same thing as a to the x times b to the x. That power essentially distributes. Okay, so something important to keep in mind as we're working through that, but that's a general idea there. Okay. Hopefully that makes sense so far. I wish I could ask for questions, but this is an online format, so I can't do that as much. That is okay. So we're going to go and move on. Okay. Now, I want to give online people here the same experience as we had in class. So I'm going to take a bit of time and we will kind of get some colors going here so we can lighten up our picture a little bit, make it more interesting. But what I'd like to do for now is kind of graph. I'll make this a little bigger. I want to make a graph with all of these kind of various exponential functions so we can get a general idea of what's happening. Okay, so we're going to start off, right? Earlier on the last video, you should have seen we did have a graph of what e to the x looks like, which is going to look maybe something like this. We'll let this be our basis. This is y equals e to the x. Okay, so let's see. We'll mark some points here. This is 1. This is -1. So this is the point e to the -1. This is 1. And then this is e. So we'll make sure to mark that so we know where we're going. E to the -1, remember, is the same thing as 1 over e, right? I just can flip that to the denominator so I get that. Okay, now we're gonna work with 2 to the x, right? So I want to figure out y equals 2 to the x. So I'm going to take these same 3 points kind of to demonstrate what's going to happen with this function. So first, let's take when x is 0. That's going to give me 2 to the 0 power, which just like e, remember e to the 0 is 1, and that's just because, right, the natural log of 1 is 0 and they're inverse functions. 2 to the 0 is the same thing as the number 1 as well. Every number base to the exponent 0 is going to be the number 1, so I can go ahead and put a blue dot right there. Okay, if I do x is 1, I'm not going to get e now. I'm going to get 2 to the 1, right, which is just 2. So, just as a reference point, and hopefully we'll have time to talk about this at the end, but e is the same thing as the number of approximately 2.71828 for reference, okay? So 2 is smaller than e, and this is the e line here. So I'm going to make sure that we label kind of a 2, I'll call this number 2 here, so it's going to be about here. Okay, so what we're seeing right now is we have the graph is going to be a bit slower than the e to the x function here. Okay, But let's look at the x is -1 piece, where we're going to get 2 to the -1 power is 1 over 2. Right? Now 1 over 2, right? Let's think about 1 over 2 versus, and maybe I need to fix my picture a little bit here, versus 1 over e. So I'm gonna let you think about that real quick. I'm gonna fix my picture just to make sure everything looks as it should. That's good. That'll be good. Okay. So just the fix is just I'm gonna move this point down a little bit. Here's 1 over e. Okay, and the reason being, right, if you've had a little bit of time to think about these two values, you should recognize that this one is going to be bigger. And the reason being is because while e is a bigger number than 2 is, right, with our approximation, because we're doing 1 over these numbers, 1 over e, since e is bigger, is a smaller number, and 1/2 is bigger. So I'm going to put 1/2 about here. So that's going to give us a point about here. Right, so what's going to happen is something like this. Okay, so before the y-axis, right, we're kind of increasing. You know, it's definitely a little higher than e is. So it's a little slower in terms of its increasing. It took a little while, and it's still slow afterwards. But e picks itself up after, so it kind of moves faster. Okay, so here e is the lower part and 2 is the higher, but then it switches after 1 as e is just a bigger number, so it grows faster. Okay, so hopefully that kind of makes sense. You can kind of get a visual graph to do. Similarly, if I were to do 3 to the x, which would be, I'll use this kind of purplish color here. Hopefully it comes through well. Let's see, that's about 3 here, put 1 here, and put 1 about here. Okay, we're gonna get something that kind of looks a bit like this. Right, so notice that 3 is bigger than e, so it's above the red line here, but it's below the red line at this portion. Okay, so we're kind of getting a visual aid of what these b to the x graphs are starting to look like. A funny one to think about is the graph of, let me get a good color real fast. The graph of, no, that's a bad one too. Graph of y equals 1 to the x power, right? Now that is just, I mean, anything, if I take 1 and raise it to any power, it's still 1. So this is literally just the number 1, so it is just a straight line, right? And so what we're seeing, what you would see is if we continue to move like our b, say like 1.5, 1.1, etc., it's going to continue to move down here, get closer to this line, and move up and get closer to the line until it kind of hits it. And then after that point, my graph ends up flipping over and changing when it hits. So basically we have numbers greater than 1, right, that we just did. We have number 1. And now let's talk about numbers that are less than 1, right? So let's talk about the graph of, let me find another color to use. We'll try green. 1/2 to the x power. Okay, so if I'm doing 1/2 to the x power, right, and I do kind of use these same 3 values, I'm still going to be hitting 1 at 0, right? But now if I put 1 in, I'm not going to be above this line, I'm going to be below it, because 1/2 to the 1 is 1/2, right? So that's going to put me here. And then if I do 1/2 to the -1, I can take that -1 and apply it to each term, which doesn't affect this 1, but what happens is this 2 to the -1 is going to come up. So essentially the fraction flips over, so it gives me the number 2. So that's going to put me here, and then my graph is going to look something like this here. maybe not quite exact compared to what I have already, but the general idea is there. So what we have essentially is just we've taken 2 to the x and reflected it over, and that's what this is, right? It's so if I have 1 over 2, it just reflects what happens with 2 because it's all flipped around, right? And similarly, can't speak, if we were to talk about 3, let's see what color I haven't used yet here. Use like this light green. I think that'll work. We've gone a little out, but that should be okay. We would see a similar trend, right? -1 would give me 3, which would be up here. 0 would give me the same number, and then 1, that would bring down to like 1/3. So we would get something like 3 to the x, but just flipped over, right? So whenever you're graphing these, this is what we should be expecting. This is kind of what we're looking for, and this is just a nice picture kind of plotting all of these together, okay? So hopefully you kind of have a grasp on what this function is doing, how it works, kind of what to do with it. Okay. Try to leave that up for a bit so you can kind of take it in, but we'll go ahead, and you can pause the video as well if you want. But in the meantime, I'm going to erase this, and we need to move on. Ooh, that light green's not erasing very well. Anyway, let's move on to find the derivative of the general exponential. Okay. So I'm finding the derivative of just b to the x power now. We did all these kind of examples looking at it. We want to find the general derivative for all of these. And the way we're going to do that is, right, it's kind of hard to tell at this moment. Similar to e to the x, you might guess that it turns into b of x somehow, b to the x power somehow. And we're on the right track, but we need to make sure we're doing the correct thing, right? So what I'm going to do is, like from earlier, I'm going to rewrite this as e to the x times the natural log of b, right? Keeping in mind, b is a constant, right? So this natural log of b is a constant. So I basically have a number times x. Now, what is the derivative of e to the constant times x? Well, we remember from the last section that the derivative of e to the x is just e to the x, so I just write down the same thing again. But then chain rule tells me that I multiply by the derivative of the inside, quote unquote, which is just the exponent here. So it's going to be the derivative of x natural log of b with respect to x, which is just going to be natural log of b. But for simplicity's sake, let's not leave this e here. We know this is b to the x, so we're left with b to the x times the natural log of b. And this is my derivative. Okay, so this is the derivative of b to the x, is how I find it. So it's very similar to e, right? And in fact, if you put e in here, right, e to the x, natural log of e, natural log of e is 1. So it works out as it expects to, right? Or you expect it to. But we can use this to kind of take derivatives and play around and kind of figure all this out. So yeah, it's fantastic. So let's do an example, just a quick example with that, right? So let's do, I think I did a couple examples in class, so we'll try to do a couple here. So the first example we'll do is I'm going to have the derivative, I want to find the derivative of 2 to the tangent x power. Okay, 2 to the tangent x power. So what do I do? Well, right, we know that the derivative of b to the x is b to the x times the natural log of b. Okay, so I want to take this derivative, right, using this, right? Now, I know we have x here, right? And we have tangent here, but for now, we're going to treat this tangent sort of like our x in this case, right? Because we have a big picture, it's this 2 to the exponent, right? Now, when I'm taking the derivative of this thing, right? According to this rule, I have 2 to the, if I have 2 to the x, then the derivative is going to be 2 to the I'll put quotes here, x, right, times the natural log of 2, right? But of course, we don't have x here. We have tangent of x. So we get 2 to the tan x times the natural log of 2. But then we have to multiply this by the derivative of tangent, which is secant squared. For some reason, many of you enthusiastically know that, so I appreciate it. In the class at least, so there we go. So that is the derivative, okay? So it doesn't matter what the b is, right? As long as it's greater than 0, of course. It always follows the same format. So if I gave you 3 instead, you would just have 3 here and 3 here, right? That would be the only thing that changes, okay? So that's not too bad of an example. I'm going to make some room real quick, and we'll do another one. Okay. Here's another example, which is going to be, so we ended up changing of the problem in class to a quotient rule problem because I want to make sure everybody remember how to do this, right? So I'll go ahead and tell you what the quotient rule is here. If you don't remember, we had to talk about it in class a bit, but essentially what ends up happening is when I take the derivative of this function, I'm going to have the derivative, right? Or let me write the general format on the side here. So we have the derivative of f divided by g. If you remember, one student in class said, you know, and most of you guys might have learned it this way, you take low d high minus high d low over low, or some people say low squared, whichever you prefer, right? But what that all means when we say low, so we're taking the denominator times the derivative of the high part, the derivative of the numerator, f, minus high, so which is f in this case, the numerator, d low, or the derivative of the denominator, right, the low part, g prime, over low, 2 lows essentially, you do g squared on the bottom. Okay, so we're going to carry out that exact thing here, right? So let's go ahead, let's think about doing 7x cubed separately, so maybe I'll do that in a different color just for fun. So we're going to do the derivative, let's think about 7x to the third power, right? So similar to the last one, right, when I'm taking the derivative of 7x to the third power, remember, the derivative of b to the x is b to the x times the natural log of b. So if we want to treat it like x first, think about it like x, right, in the multiply change rule. So in this case, we have 7. So I'm going to have 7 to the x cubed. I'm going to write that again, right? This is kind of our x in this case, times the natural log of 7, okay? So just directly applying this rule, I get 7x to the third times the natural log of 7. But then I have to multiply on the end by the derivative of the numerator, or the exponent here, right? Which is x squared. Right, so this will be the derivative of my numerator, right? So we're going to carry this into our problem. So we're going to get, right, low, which in this case is x, d high, so d high is 7x to the third power times the natural log of 7 times 3x squared, minus high, right, minus f, 7x to the third power times the derivative of the bottom, which is just 1, right? All over the bottom squared, so we just get x squared. Now you can feel free to simplify it down or pull out a 7x cubed if you want to, but that is our answer. Okay, so hopefully that makes sense. I'm really sorry if it's a little blurrier. I hope you're able to follow still and get the general idea. I just can't really get the best lighting here, unfortunately. It satisfies at least, so that's good. Okay. Fantastic. So, I thought what we discussed in class and what I want to cover here, right, is we need to be very careful when we're working with exponentials. So I'm going to write down a few cases, right, to help you kind of diagnose, you know, what do I do in the case of this exponential. And I think for the sake of those online here, I kind of described this in class, but I'll try to make it a bit more concrete. To help you, we're going to have 4 options here. The first option is where I have some base, which I'll call b, just the number b. These are numbers. And I have an exponent, which will be n. So I have b, some number b raised to some number n. And I want to know the derivative of this thing. Okay. So if I have a number to a number, right, that's just a number. What is the derivative of a number? Well, it's 0. So that would be it. Okay, so that's the first one. The second one is the derivative of, now I'm gonna have this, sorry, I can't speak. I'm not gonna have this base b now, but instead I'm gonna replace it with x and raise to the n power. Okay? So when I take the derivative of this, right, this should remind you this is our normal power rule. And normal power rule says that I take the power, which is n, multiplied in front, times x, and then raise that to the n minus 1 power. Okay? More in general, if you want to have it, if I'm taking the derivative of like a function, right, to the n power, then we have to use chain rule where we say n times f of x to the n minus 1, and then we multiply by the derivative, right? But this is sort of like our base case, like kind of the easiest idea to see. Okay? The third one we just talked about, which is where I don't have a variable in the base now. I have b again. I have this base b again. But now I have an exponent, or sorry, I have a variable in the exponent. So I have b to the x, right? And we just talked about this. This is b to the x times the natural log of b. Okay? Really try not to get these confused, right? Here are the variables in the base, and here are the variables in the exponent. Okay? You should be able to see that you're kind of working through it pretty easily, but just try to be careful. Don't try to do x times b to the x minus 1 or something and get them too confused. Okay? And again, there's a general case. If I have d over dx and I take b to the f of x, then this is going to be b to the f of x times the natural log of b, and then this is multiplied by f prime of x. Okay. Finally, it's the last case where I have an exponent in both the base and the exponent. Now, we've done this one in class. We did it yesterday. This is x to the x times 1 plus the natural log of x. Right? Where we found that one, but we didn't even really use either of these rules. We ended up using logarithmic differentiation. So I would encourage you to look that up again, but essentially, right, remember, so I'll try to remind you from this case. If I wanted to find the derivative of this thing, I first took the natural log of both sides so I can bring the power down. Okay, to get something like this. Now again, this does have a, you can kind of think about this more broadly where I have some function to another function. Obviously, I can't write down a general formula because it gets a little complicated, right? But in general, you just need to take the natural log to kind of bring powers down, and then you can work it out from there. You can also use a similar idea where we took, right, we said b to the x is e to the x ln b, and apply it here. So I could do like the derivative of e to the g of x times the natural log of f of x. If you can see that, so the natural log and e would cancel out and the f of x would come back down. But this gives me kind of the same idea I would get here. I would just be working with e instead. Either is fine. It still falls to that logarithmic differentiation idea, but yeah, just choose. Sometimes, a lot of times, people they prefer, like most students prefer to do this one, so that's completely fine. Okay, fantastic. So, do that for a moment. Okay. Speaking of logarithms, that brings us to the second piece of our section here, which is the general logarithm, right? So what do we do with this? Well, actually, want you to miss out. I gotta give you just one more thing about this. I gotta give you one more special thing about this guy, okay? If that's okay, if you're permitting. Okay, so remember with in 6.3 we learned that e to the x dx is e to the x plus c. Well, we also have another formula that will work with b to the x, right? So as you might guess, it involves b to the x in some way, but let's kind of think through it, right? Remember, the derivative of b to the x equals b to the x times the natural log of b. So naturally, right, if the derivative of b to the x is b to the x ln of b, we should know that the integral of b to the x ln of b is b to the x, correct? And make sure to put the dx in there, right? This natural log of b is constant, so I'm just going to pull it outside. So I get the integral of b to the x dx equals b to the x. And then, of course, there's like a plus c on here, but we don't need to worry about it too much, especially after dividing. So I can take that natural log of b then, right, and divide it from both sides. So that tells me, maybe I'll write it here, this is equal to b to the x over the natural log of b plus c. So essentially what happens is on the derivative you multiply, but on the integral you divide by the natural log of b, right? So maybe we'll just do like a real quick example of this, just to kind of get it understood. Oh no, I think I remember which one we did. Okay, so the example I did in class was, like, just to kind of demonstrate this real fast, this rule, we can take the integral of 2 to the square root of x over 2 square root of x. Looks kind of funny, I know, but try not to let it trip you up too much. Dx. Okay, so what do I do in this instant? Well, let's think about it, right? I need to be able to solve this, and this looks a little difficult, right? But we don't really have a lot of integral techniques yet, and won't until next week. So let's try to, I don't know, try to break it down a little bit, right? So I'm gonna see I have a square root of x in the exponent here, and that's causing me some trouble. So maybe I'm gonna do a u sub here. U is gonna be the square root of x. And remember, to find the derivative, right, because we need du of the square root of x, I need to write it as x to the 1/2. But when I do that, I'm going to get 1/2 times x to the negative 1/2. But that negative is going to bring it down to the denominator. And of course, again, as I said, x to the 1/2 is the same thing as square root of x. So if u is the square root of x, then du is going to be 1/2 root of x dx. What do we have? Well, we have 1/2 root x dx, don't we? So this works out really nicely. So maybe I'll draw like a little equal sign here. This is going to be equal to the integral, right, of 2 to the u power, and then all of this, right? Maybe I'll emphasize again. So I'll circle this guy. Oh, that works. Circle this guy. Circle this guy. These are the same, right? So I can just substitute all of this for du. So I get 2 to the u, du. We just learned, right, that the integral of b to the x dx, or in this case is 2 to the u du, still works the same way, is going to be 2 to the u over the natural log of 2 plus c. But u is the square root of x, so we get 2 to the square root of x over natural log of 2. There we go. So that would be our answer. Okay. Hopefully that made sense. Again, there's a lot of u sub going on here, so just make sure you're keeping track of that. Watching out, otherwise it's not too bad. Okay. Do that for a moment. That should be good. So I hope you enjoyed that little tangent there. Not much of a tangent, you didn't need it, but anywho, okay. So now logs, right? So if I have y equals b to the x power, I have this thing defined, right? It's a one-to-one function, right? We saw all the graphs, aside from 1 to the x. 1 to the x definitely is not, right? It's a horizontal line. So anything but that is a one-to-one function, right? So it has a natural inverse, and that inverse is represented by, I'm going to write x, right? Which, so the logarithm, the exponential, is equal to log base b of y. Okay? So the function we're wanting to look at now is a function where we have log base b of x. Now, I hope you're not too confused by the variables. I just need to do this to kind of show how these are related to each other. Saying that this statement is the same thing as this statement, essentially. If you swap the x's and the y's and x's and y's here, it'd be the same thing. Okay? So like x equals b to the y implies that y equals log base b of x. Okay? So this is a function we're wanting to look at. Okay. So let's think about this, right? I'll go ahead and say, if you have guessed it, right, just based on the exponential part, the rules for this logarithm are the exact same. They do the same thing. Nothing has really changed in that department, right? So we're going to have, log base b of xy equals log base b of x plus log base b of y, and then log base b of x over y equals log base b of x minus log base b of y. And finally, if I have log base b of x to the r power, then we're going to have r times log base b of x, just like that. Okay, so these rules still apply. I don't need to worry about proving them too much. They're really fairly simple once we talk about another key element. But all the rules are still here, right? Again, I'll kind of get to that in a sec. But first, let's kind of talk about graphing these, right? Let's see what they look like. Okay, so naturally, right? Remember, let's look that in a bit. Yeah. Remember, we're talking about inverses, right? All you need to do is kind of take the graph of the function you have and then just flip it over the line y equals x, and that'll be my new graph, right? And similarly, we get the same idea here. So, but let's kind of talk about, so natural log, if you remember, is going to look something like this. So we'll say this is our y equals natural log of x, right? But let's say you don't have 2 to the x to kind of easily flip over. It's a little harder to do it. So let's kind of work through it, right? Let's talk about, and I want to try to keep it consistent with my colors here. So we're going to take y equals 2, what? So y equals log base 2 of x, right? So remember that when I write speak today apparently. When I write log base b of x, right, I'm saying, right, natural log, we're talking about how it's related to e. Its base is e, right? So everything is based off of what happens with e. But now when we're looking at log 2x, everything is based on 2b, the base. For lack of better words there. So how do we graph this? Well, we can get some points, but we want to kind of think through it. Okay, so let's talk first about, let's do an easy one, right? I want to figure out what happens when x equals, okay? So when x is 1, right, I have log base 2 of 1. Now, what does that equal to? Well, remember, and I'll write this again. So if I have log base 2 of x, right, equals y. This is the same question as 2 to the y power equals x, right? So that's the same question. So whenever I'm asking what log base 2 of 1 is, this is the same question as 2 to what power gives me 1, right? Now, as we've kind of talked about with all the exponential, we should know, oh, well, 0 gave us 1 for all of the gave us 1 for all the exponentials, right? And that's absolutely right. So this question mark here is 0 in this case. So just like where this natural log hits, we also have a point. Okay. Now let's do x is 1/2 next. Okay. So I have log base 2 of 1/2, right? So my question is 2 to what power gives me 1/2? Well, that'll be -1, right? So whenever I'm at 1/2, I should be down at -1, which would be one moment here. I need to fix my graph again. Just terrible again this first. I have to figure that out first try. So let's. Okay. Did the same thing again. Just at least I'm consistent, right? Gotta give myself credit. Okay. So whenever I have y equals 1/2, I should have. Sorry, I just placed that. Y is 1/2. I should have x, or I should get y to be 1. So I'll put that about here, just to kind of demonstrate the idea. There we go. And then let's try x is 2, right? So this one's even easier. We have a log base 2 of 2. So this is the same thing as asking 2 to what power gives me 2. Well, clearly that's number 1, right? So that's going to put us above here. So our function is going to look something like this, right? Now, I will affirm to you, anytime I have log base something of something, right? So if I have log base 3 of 3, log base 4 of 4, it's always going to be 1, right? Because you're just asking, you're just saying, oh, that number to the first power is that thing. So it works out nicely. But this is the graph. So this is a graph of log base 2 of x, right? And maybe to save some time, we'll just kind of work through all the rest here real fast. So let's talk about, if I have log base 3 of x, I'm going to get something that looks like this. So this is log base 3 of x. We don't actually have a 1 version here, right? Because you're saying, let me just give you an example of why we don't have log base 1 of x, right? Let's think about it. Any number, I'll take 2, right? Log base 1 of 2, right? This is the same question as 1 to what power gives me 2? What power can I take 1, 2 to give me 2? There is a 1, right? So I have a lot of issues here, and that's why we can't really match that one here, but that's okay. We'll go to move on to our fractional parts then, right? So let's do log of 1/2 of x. Log of 1/2 of x. And I think I did that in green. Yeah, that one. So I'll write that log 1/2 of x is in green. So remember, when x is 1, we get 0. So that's the same point. However, right, let's just run through some quick ones. If I take x is 1/2 now, right, I get log base 1/2 of 1/2, which just like down here is just going to be 1, right? Because it's 1/2 to the first power, it's 1/2. So that's going to actually bring me upwards to about this point. Or sorry, to 1, right? So I need to go up here. Awesome. Okay. That seems about right. And then if I take x is 2, right? I want to say log of 1/2 is 2. So the question is 1/2 to what power gives me 2? Well, if we kind of refer to what we were thinking about earlier, this should be -1, right? Because I just want to flip the fraction. So when I'm at 2, or when I'm at 2, I should have -1. So it should be down here, right? So we're getting this sort of graph like this. So again, it's just you take the blue graph and kind of flip it over. So it works out pretty simply there. Maybe I'll take this brown real fast. So we can do. I'll write log of 1/3 of x. Again, it's very similar. It should. Let's see. Maybe we'll think about it real fast here, just make sure we don't make any mistakes. It's gonna slow down a little bit here, but it's definitely going to. Yeah, it's gonna be below. Right, matching up to that purple line. But this is log base b of x, right? These are kind of the different variations, the basic cases, right? and this is what we should be looking for. This is kind of what you're graphing when you do this, okay? So really study these examples, think about these, and kind of practice them, work through them, and it should help you out a lot. So, okay, let's work on trying to wrap this up here, right? I don't want to keep you for too much time. So, the burning question here is, I want to do calculus. I want to do calculus with this thing, right? I need to do calculus now. Calm down. I know you love calculus a lot, but we'll get to it, okay? We'll get to it. Let's take a first step, okay? You may remember in your previous class that if I have log base b of a, okay, so I have this logarithm with log base b and it has a in it, and I want to change the base of this, right? So rewrite it with another logarithm. The way I would do that is I would take log base c of the argument, basically the thing on the inside, a, over log base c of the old base, which is b, and I get this. Okay? There's a little proof in the book that kind of does the natural log case. I won't mess with it here, but this is the idea. Okay? So what I'm going to do is I'm going to take log base b of x, but I'm going to rewrite it using natural logs, right? So essentially, I'm going to use natural log of x or log base e of x. It's the same thing. So wherever you see log c here, I'm going to use natural log instead. So log base b of x is the same thing as the natural log of a, which in our case is x, over the natural log of b, which is the base. And so this, similar to what we did with b to the x as e to the x on b, we have something going on here, right? And I think earlier I mentioned talking about the laws. Using this helps to prove those laws pretty easily, right? So if you just want to see it real quick, right? If I want to know log base b of xy, this is log base, this is natural log of xy over natural log of b, which is natural log of x plus the natural log of y over the natural log of b. But this is the natural log of x over the natural log of b plus the natural log of y over the natural log of b. What is this? Well, it is log base b of x. And what is this? Log base b of y. So therefore, it works. Okay, so I wanted to save that part, but that's kind of how we get to there. So it still works for similar reasons. So if you ever need to expand like a logarithm like that, you can do it the same way. Anyway, what I want to use this for now is I want to use this to find the derivative of log base b of x. So, in essence, instead of doing this one directly, I'm going to rewrite it as natural log of x over natural log of b and find the derivative. Now remember, this natural log of b right here is just a constant, it's just a number. So I'm going to rewrite this as the derivative of 1 over the natural log of b, so that's just a number, times the natural log of x. What's the derivative of natural log of x? It's 1 over x. This is a constant, so it just sticks around. So we get 1 over the natural log of b times 1 over x. Or, more formally, we like to put it as 1 over x times the natural log of b. So, extreme right, extreme left, extreme right. There you go. Okay. Awesome. So hopefully that makes sense, right? You kind of track with that. What we're going to do now is we're going to do an example, right? So again, the derivative of log base b of x is 1 over x times the natural log of b, right? You're seeing a lot of natural log of b in this video, I'm sure. And you're probably tired of it, but stick with me, we're almost done, okay? So I'll write this rule, we'll rewrite it. So the derivative of log base b of x equals 1 over x times the natural log of b. Okay, so let's do a quick example. And the one I did in class was log base 7 of x cubed plus x. And I want to find the derivative. we have log base 7 of x cubed plus x. Now, these do both technically have an x in it, so I could try to factor it out and maybe like split this up, but we don't need to worry about that here. This function isn't too complicated in itself, so it should be okay, right? So, to take the derivative of this, right? Let's first, I'm going to treat, this is a good one, yep. I'm going to treat this as x, right? Just kind of think about it as log base 7 of x, and I'm going to work it out that way, right? So the derivative of log, so again, I'll write it up here so you can see it. Log base 7 of x, right? Using this formula is going to be 1 over x times the natural log of 7. So we have that, right? And so that's going to carry over here, right? But instead of x now, we have x cubed plus x. So this is 1 over x cubed plus x times the natural log of 7, right? But obviously to counteract this, kind of fix it, I need to use chain rule, right? And chain rule tells me that I need to multiply by the derivative of x cubed plus x, which is indeed 3x squared plus 4. And so this is my answer. I'll leave that as at one example for now. A lot of these examples just become very similar to the natural log and e to the x with the b to the x part, except you just have to worry about these natural logs. So really pay attention to those. Be careful. You got it otherwise, okay? You know what? I hope I didn't confuse anybody. This is supposed to be 6.4 star. Uh-oh. Might be a train passing here. It's just my apartment, so that's just, you know, things happen like that sometimes, so it's fine. Anyway, let's go ahead and finish this up with a little bit of discussion here. This is basically the end of the lesson. The book talks a little bit more, and so I will as well. You know, if I had the students in class do it, that doesn't mean you're going to miss out. So. At the beginning of the 6.3 lecture, we talked about this number e, defining it as the number that makes the natural log equal to 1, right? Which that isn't very concrete. That doesn't really tell us much, right? Now we define the natural log and we've defined like e is the inverse, right? But we still want to nail down, how do I calculate this number? What do I do to calculate this number? And the way we're going to do that, the way, you know, we can do that is through a little bit of derivative tricks. So let me demonstrate. So I'm going to start with my function, which is the natural log of x. And I'm going to have the derivative, right? What's the derivative of the natural log of x? It's 1 over x. Now, we have our rule, right? We have a rule to do that. We know what it is now. But let's kind of go back a bit and return to our limit definition of the derivative, right? Which we talked about yesterday. Being reminded of it is the limit as h approaches 0 of f of x plus h minus f of x all divided by h, right? Which there's another one which we talked about, but that one's not as relevant here. We'll just do this. Okay. So what I'm going to do is I'm going to take f, of course, as ln of x and 1 over x, but I'm going to evaluate it specifically at 1. So we're going to get the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h, right? Now, we'll come back to this side, but let's worry about this right side for now. F is natural log of x, right? So we're going to get here, we're going to get the natural log, the limit as h approaches 0 of the natural log of 1 plus h minus the natural log of 1 all divided by h. Okay. Natural log of 1 is what? Well, it's 0, right? Probably should have mentioned this at some point by now, but this is going to be 0. Okay? So we're left with inside here, we get the limit as h approaches 0 of, now I'm left with the natural log of 1 plus h, right? But I also am dividing by the h. But what I'm going to do is I'm going to take that h on the bottom and I'm going to bring it to the front as 1 over h. Now my goal here is I want to take this natural log here, right? And I want it to kind of overcome, I want it to be in the front, right? I want everything to be inside the natural log. Okay, I want the natural log of just something over here, not 1 over h times. So what I'm going to do, right, is remember, if I have the natural log of x to the r power, this is r times the natural log of x. But this also works the other direction. So I'm going to take this 1 over h term and I'm going to bring it inside. So we get the limit as h approaches 0 of the natural log of 1 plus h to the 1 over h, right? 1 over h power of that. Okay, fantastic. Now, one last thing here is the natural log is a continuous function. And what that means is that I can neatly take my limit and kind of phase it through the natural log and bring it into function, right? If you want to talk more about that with me later, we can, just to kind of review it. But you should have experienced kind of talking about something like that during your Calc 1 class. But what's going to happen is we're going to get the limit, I'm going to have the natural log, so this is equal to the natural log of the limit as h approaches 0 of 1 plus h to the 1 over h. Okay, so this thing right here is equal to f prime of 1. Well, we know f prime. It's 1 over x. And what happens when I put 1 in there? I get 1. So this tells me that the natural log of the limit h approaches 0 of 1 plus h to the 1 over h equals 1. I want to get that limit by itself now. Why? How do I get rid of this natural log? We cancel it out. We're going to put both of these sides, both the left side and the right side, on e as the base. So the natural log and e cancel. We have e to the first power. So this is going to be the limit h approaches 0 of 1 plus h to the 1 over h. Okay, let's make some room on the board and just like proclaim this a little louder, right? Let's talk about this. The limit e is equal to the limit as h approaches 0 of 1 plus h for h. So if I take this thing quantity to 0, then I'm going to get the number e. Another way to write this, right, instead of h, maybe we like x a little better, so I'm just going to replace all those h's with x's. And I get 1 plus x to the 1 over x. Same thing, doesn't change. Another possible option too is instead of having x 1 plus x to the 1 over x here, maybe I want that exponent to be a little nicer. So I'm going to replace all these x's with 1 over n, which in turn I'm going to change my limit to as n approaches infinity. Okay, again, feel free to talk to me about this. This isn't as big a deal to transform this, but you probably would have experienced something similar to it in the past. But I'm going to write this limit as n approaches infinity of 1 plus 1 over n. This is probably my favorite form to see it in, favorite form to work it out. But all three of these can be expressed as a number e. Okay. So after all that work, we finally reached this point. We finally know something about e. We've done a bit of work defining logs, exponentials, and all the rest, but we've we finally nailed something down. So, thank you for listening. Next time, we're going to be talking about applications of the exponential and the logarithm to some real world problems and kind of what that means for us. And after that, we'll be doing L'Hopital's rule for limits. So, thank you for watching. Hope you have a great night. Sorry I didn't record. I need to get better at that.